condition if there are no pebbles? Atmospheric pressure should be equal to pressure of gas, isn't it?
Just the pressure inside the piston.
But if you put the pebbles, let's say this is our initial condition, then what is
Yes.
P gas equals to?
Yes.
Tell me, what is P gas?
The pressure exerted by these and the atmospheric pressure.
So how you calculate the pressure exerted by these particles? अरे you have qualified JEE, you are a chemical engineer. थोड़ा सोचो. Weight of particles divided by
Yes.
what? This is force, right? Divided by what?
Yes. So force upon area, sir.
Area of piston. Okay.
Is the piston.
Yeah. Fine. Cross section area of piston. Okay. So now if you will remove Shashank, these pebbles or very small particles one by one, what will happen? Every time you will deviate from the equilibrium slightly.
Yes, sir.
Right?
So at
And
every situation we will gain equilibrium.
Yeah, so when you remove the particle, it will go to a new equilibrium.
Yes, sir.
Right, deviation. So gas pressure will be changing, right, every time, but through equilibrium steps. Okay.
Yes,
so
sir.
gas is expanding, right?
Yes.
So let's say if you remove one particle and there is a movement by delta A, dx, if you put that particle back, what will happen? So when you remove one, let's say when you remove one particle, you are removing, what will happen? Piston will go up or down?
If we remove, then piston will go up.
By distance dx, right? Now you put back that particle.
Yes.
Okay. What will happen?
So it will try to go down.
Why try? It will go down. If you ignore all the losses, it will go down. So reversible work transfer for both system and surrounding is possible. We can, but for heat transfer it's difficult. For work transfer it's possible if you ignore all the losses.
Yes.
If you ignore all the losses. Okay. So that's a reversible work transfer process. Since we are discussing this, let's now, thanks Shashank. Huh? Never mind when I take the name, it's my way to, interact. So don't think so much that you answered well, don't worry. So work reservoir. So how we define thermal reservoir? Anyone? Let's say Ayush, how you define this thermal reservoir? Yes, Ayush. Acha, our dear friend Ankit is there. Ankit Verma?
Yes, sir, I am here.
Yes, Ankit. So you are back to studies?
Yes, sir, I am back.
Great.
Sir.
Do you know what is thermal reservoir?
Hello.
Yeah, what is thermal reservoir?
Sir, actually, I have missed the last class. I will read recordings.
Just a very honest suggestion. Revise it as soon as possible. Otherwise, you will miss everything. I can guarantee.
Okay. I will try to.
Don't
I will try to.
that, the grading will be very easy. Of course, grading will be very easy, but you have to score even in this online mode. And don't think problems are going to be very simple. It will be innovative.
No, sir.
Yeah. So for others, the whole class, I'll take 2 class tests. One is going to be innovative. That's the test where I will distinguish between those who are putting effort, those who are not putting effort. Another second class test will be easy. I mean, you can, from whichever source you want to solve, we solve. I don't care. One test will be innovative, where you have to put your mind.
Okay, sir.
Okay. Yeah. So see, thermal reservoir, we have seen that it's nothing but it's a body with very large heat capacity as compared to the amount of heat involved in the process, heat transfer involved in the process. So that practically you can assume that that reservoir temperature never changes, and generally reservoir is a surrounding. So that is a thermal reservoir. Work reservoir, you can say a body, okay, or a boundary, or whatever you want to say it, from where you can transfer the work. You can only transfer the work, only work transfer. No Q. No Q transfer. Okay, that is work reservoir. Simple example of work reservoir is in this spring piston system. If you will compress the spring and gradually if the spring will be released by maintaining the equilibrium, then spring can only transfer work to the piston, nothing else. Means spring can transfer work only to this gas trapped in the system, nothing else. So spring is an example of work reservoir. Okay, a shaft like a mechanical steerer, when you rotate it, it can only transfer work. Then work get converted into heat, that's a different thing. But a shaft, this kind of shaft can only transfer work, only work transfer. So this is also kind of work reservoir, only work transfer. Okay, fine. When we'll do example, it will be more clear. Perfect. Now, before now we go to the next topic, just to remind you that what we are looking for, we are going through second law, and the main target of second law is that we are looking for the lost energy rather than lost or unavailable energy. That's fine. And we have seen from our primitive definition of entropy or unavailable energy that it is related to entropy. We still do not have any definition of entropy. Remember, we have not defined entropy or change in entropy. We don't know what is entropy equal to what. But that's where we are heading. This whole discussion is going there. Okay. So we know that it's somehow related to lost energy or unavailable energy, and this unavailability come into picture due to irreversibility. So somehow at the end we should be able to connect these things, irreversibility. So at the end we should be able to connect this. So keep this whole thing in mind, that what is our goal. That second law talks about irreversibility of a process. Okay, and it also talks about unavailable energy, and somehow it is related to a property which we named as entropy, but we still don't know what is the definition, like mathematical definition of entropy. Still we don't know. Now on this, since we are saying that we don't know the definition of entropy, remember there are two paths which people have followed to define entropy. One is which we are studying, classical thermodynamics. So we will see that how we define entropy here, but no physical explanation here. Classical thermodynamics doesn't provide any physical explanation of entropy. No. What it explains is this lost work. It will explain lost work, because when we do the experiment or when we do the real process, when we see the real process, there is lost in available work or available energy. Sorry, lost in available energy, which we know as potential to do work. So classical thermodynamics has chosen that definition of entropy in such a wise manner that it explains lost work, it explains irreversibility. Okay, but there is no physical explanation, or more precisely, no microscopic explanation. What is a microscopic mechanism? What is happening in the system? Classical thermodynamics can't explain this. So once we will finish this approach of classical thermodynamics and we'll define entropy, which Clausius did, then we'll go to more insightful or more fundamental approach to understand entropy, that is statistical thermodynamics. So I will give just small journey of the, we will just travel for some time in this domain, statistical thermodynamics. There you will get the microscopic origin of entropy. Although you will be surprised that classical thermodynamics came first. So the entropy definition was already there in terms of macroscopic variables like heat, temperature. Later on, people have explained it through this approach, microscopic approach. So as I told you that if you want to just feel this thing, these two approaches. The simple example is that before all the kinetic theory of gases, people were knowing pressure. What is pressure? People were measuring pressure also. People were measuring temperature also. But then, so that is classical thermodynamics approach. You are measuring the macroscopic variable, and then you are defining some laws like PV equal to nRT, Charles law, Boyle's law, temperature. So that is classical thermodynamics approach. But when this statistical thermodynamics came, where you go to kinetic theory of gases, and then you do the averaging of velocity, and then that averaging of velocity you define as temperature. Similarly, you go to this, the particle transfer, the momentum transfer by the particle to the wall, and then you take the average, and then you come out with expression of pressure. So that is microscopic explanation of pressure and temperature. So of course, this whole insight related to this thermodynamics came this statistical thermodynamics came later, after classical thermodynamics, just to explain the physical origin. Classical thermodynamics only talks about what we observe, how we can explain them in terms of equation, like macroscopic variables. But statistical thermodynamics gives us more insight about the phenomena. So with this small, preface, let's move. Okay. Yeah. So this, I think this slide is important. Keep these important things in mind, that you should know where we are heading. Okay. Great. So if you remember, this slide is important. Those who missed this, please go through this slide. This is the summary of what we have learned till now. We have seen that the maximum work can be, in the beginning also I have discussed an example, same example I repeated in the last class, that if you are going from state 1 to state 2, then the maximum work which can be obtained from the system is that if you are going from 1 to 2 reversibly, if system is doing work. If work is being done on the system, then you have to do smallest amount of work if you do it reversibly. Okay. So W by system, okay, W by system irreversible is always less than W reversible. Okay. So maximum work can be extracted when you do this process reversibly. Now let's go to, again, we will get back to our what we call heat engines. Okay. So we have seen that what is heat engine. Heat engine, if you remember, there is a source, means thermal reservoir at high temperature. There is a sink. Heat engine is a device which works in a cyclic manner. So process is cyclic. We have seen that how heat engine works: compression, expansion, compression, expansion, heat taking, heat loss to the environment. Okay. So basically, heat engine does some useful work. Okay, that's what we do. Now, today we are going to first, so there should be a reference point. So today we are going to start with Carnot cycle, and you will get to know the reason why. Basically, Carnot cycle is a reversible cycle. Okay, so let me share another PPT. And why we need to define this reversible cycle, you will soon get to know that why. Okay. So here you can see the Carnot cycle. Carnot cycle is nothing but, or you can say it's Carnot engine also. It's nothing but Carnot engine follows Carnot cycle. It follows Carnot cycle. I am very sure you all are aware what is Carnot cycle. If you see the PV diagram. So if you start from 1, so you expand the gas expand isothermally, okay, from 1 to 2. Since gas is expanding, gas is doing some work. And if it's isothermal, if you want to keep the temperature constant, of course you have to provide heat. So this is the step where you provide heat, right? QH. And how you provide the heat? By keeping the, so you can see the right hand side diagram, by keeping this gas piston system or engine, whatever it is, in contact of a thermal reservoir at high temperature TH. Okay, you are doing it reversibly, very slowly. So QH is getting transferred in small steps. So it's a reversible heat transfer. Okay. So this you can see 1 to 2 is isothermal expansion. then it's adiabatic expansion. Okay, since it's adiabatic expansion, no heat addition. So now gas will certainly lose some energy and its temperature will go down because gas is doing work. Okay, so then you come from 1 to 2, then 2 to 3, then again there is isotherm at low temperature. How you do it? By keeping the system in the contact with the low temperature reservoir. So you come to 4 and then you go to 4 to 1, which is adiabatic compression. This is Carnot cycle. Okay. So first of all, we are going to see the efficiency of Carnot cycle, and then we'll see Carnot theorem 1 and Carnot theorem 2, and then you will get to know why there is a need of defining a Carnot cycle. So Carnot cycle was defined by this great guy, Sadi Carnot. He was a French military engineer. Okay. So he has you can say what we can say, that uncomparable contribution to this thermodynamics. Let me see what was his, I mean, just a moment, let me see what was his, so his, I mean, you see 1796 to 1832. So he left, I mean, he expired just, I mean, he's like, how much years? 32, right? So 32 years there, and then here 4 years. So only 36 years, his lifetime. And within, you see that at so young age, he had contributed something which is amazing, just based on various observations. So he defined this Carnot engine, reversible engine, which is not possible, by the way. It's not a real engine. But why we need? Because we need a reference. We'll see. Okay. Now I'm sure many of you, if I'll ask you, you can derive this efficiency of a Carnot cycle. How many of you think you can do it without the knowledge of entropy and all this from your basic education, which you did in maybe 11th or 12th class? Can we find out efficiency in terms of temperature?
Yes, sir.
So it comes out to be what? First of all, how we define efficiency? I mean, I'm sure you know it. So let's define it. How we define efficiency?
Work done by heat given. Work done by heat given.
So W by system, right? That you know, and Q2 system. So in this case, which temperature? So here we have QH, and here we have QL lost. Okay. So eta should be what? The area of this cycle.
1 minus TL by TH.
Yeah. So area, yeah, fine. In denominator, what will take? QH or QL or QH minus QL? In the denominator, what
denominator we'll take QH.
Only QH. Okay? You are giving, huh? And hence, if you follow the first law, W comes out to be QH minus QL. And as someone commented, it's 1 minus QL by QH, and someone said TL by TH also. Does everyone know how we reach to this result? If someone doesn't know, please comment. I am waiting for 1 minute. Otherwise, I will just tell you the approach. It will be homework. Anyone has any problem? Feel free. Then I will do it. Otherwise, we will save our time.
Sir.
Yes.
Sir, I did not understand the theorem that was stated by Carnot. Means why?
No, we didn't do that. We have to wait. First, we are just defining efficiency of Carnot engine. Let's say eta R.
Okay.
Or eta Carnot. Huh? Okay. We haven't done that. Okay, don't worry. We'll come to that. Before that, we have to do this. So eta Carnot is 1 by minus TL by TH. If anyone has think that he can't prove it, feel free.
Sir. Hello.
I can hear you.
Sir, I had a question. So like we are getting work done by system right here. So like is that reversible work?
Yes. The whole Carnot cycle is reversible. All this, say, acha, how I have shown this lines by solid lines, right? This whole process is shown by solid lines in PV diagram. So undoubtedly, this whole all the steps are reversible. All reversible steps, undoubtedly. Okay, all steps are reversible. Yes, that's in case if I didn't say it. Yes.
Sir, so what we said that work done by system is always less than like in irreversible cases, it's
Yes,
less
we'll
than
come to
work
that.
done by
First of all, let's
reversible.
stick with reversible. This is a reversible cycle.
Sir, so this difference between the reversible work and irreversible work is.
I'm coming to that. Okay,
Okay.
I got it. You're that's the whole agenda of today's class. But Carnot cycle, if I missed it, I didn't miss it. But in case if you overlooked Carnot cycle, remember it's a reversible cycle. All steps are reversible. We are doing all the steps reversible. So this W which you are saying, it's W reversible.
Okay, sir. Yes.
Okay, this is W. Very good. This is W reversible. Okay. Okay. What does it mean by W reversible? How we mathematically take advantage of this? Whoever was asking this question, this W reversible. What is that? How we take this the advantage of this saying W reversible?
So we
So we
can
can
apply.
write the isothermal expansion work as integral PdV.
So we can write integral PdV rather than it's whatever it is. Adiabatic also you can write that work, right? Integral PdV.
Yes, sir. Yes.
For all the steps, you can write integral PdV. That's the advantage. Because you know how P varies at V, either functional form or all the points. Okay. So that's the advantage. And since that is the advantage, as someone commented, see, I am sure you have know the work done in isothermal process, that nRT, ln, V2 by V1, whatever it is. So you know work in this step. You can calculate work in adiabatic expansion also. It comes out to be, as much I remember, P1 V1 minus P2 V2 by gamma minus 1, right? So for this case, P2 V2 minus P3 V3 by gamma minus 1, and you can write it as nR T2 minus T3 by gamma minus 1, right? So basically, you can calculate all the works. Yeah, you can calculate all the work. So then you can easily get what is the work done by the system, reversible work done. You can calculate Q also. That's also not very difficult. Okay. Why? Because when you go from 1 to 2, it's isothermal process. So there is no change in internal energy. So whatever work you are doing here in this expansion, that should be equal to QH. Similarly, you can calculate this QL also, because this is also isothermal compression. So basically, you know all the quantity, and in these adiabatic steps, there is no heat transfer. So you can easily calculate these quantities. And then you have this, for adiabatic process, you have this relation also, PV raised to the power gamma constant. If you use all this and do some mathematical manipulation, you can get this result. So this I am leaving as a homework. I'll put it in the assignment list. Okay. Well, so we know that for a reversible cycle, the efficiency comes out to be, when you apply do this algebra, 1 minus, so eta Carnot, let's open a new page. So eta Carnot comes out to be 1 minus a very handy formula, TL by TH, where these are the temperature of thermal reservoirs. We will see these are temperature of what in the examples, but right now it's thermal reservoir. Okay. Great. Now let's go to Carnot theorem. As someone commented that, sir, you stated two theorems, and he didn't, of course, because we didn't prove it. So what Carnot theorem 1 says, and then we'll prove it. Carnot theorem 1 says that all heat engines, someone talked about irreversibility also, that if some engine is not reversible, what does it mean? So let's see this theorem. All heat engines between two heat reservoirs are less efficient than a Carnot heat engine operating between the same reservoirs. We know that Carnot heat engine is a reversible engine, reversible heat engine. So whatever engine you have, heat engine you have, okay, if it's working between two reservoirs, let's say TH and TL, then its efficiency will be less than or equal to the Carnot cycle or Carnot heat engine, which is operating between the same source and sink. Okay, let's prove it. It will be clear, not a big deal. So for that, let me open a new slide. I'll just paste Carnot theorem 1 here, and then we'll prove it. Only Carnot theorem 1. That's what we want to prove. Remember, we still don't know what is entropy. I mean, yes, we know there is something, but what it is, we don't know. We'll see. That's the whole agenda of the second law. Okay. So, Carnot theorem 1. So, for that, you can follow me or you can see me and later on you can put it in your notes. So, let's say we have a thermal reservoir at higher temperature T1, and then we have sink at lower temperature T2. Of course, T2 is less than T1 undoubtedly. Okay. Now let's take, we know that our Carnot is a reversible engine. So this is our engine. I am saying it R. Okay. And this is our Carnot engine, which is reversible engine. So right now assume it's a Carnot engine. Don't say it any reversible engine. Say it's a Carnot engine. Okay. I have written R for some reason, that rather than C, it's better to write R. So it's a Carnot engine. Okay, reversible engine. It takes Q1 heat from the source. It rejects Q2 heat and you get some work, and we will say it W reversible because Carnot cycle is a reversible engine. Okay. Then you take irreversible engine. Let's take irreversible engine. So for this I will write IR. This is irreversible engine. This irreversible engine is also taking the same amount of heat, Q1. Okay. And it will reject some heat which we don't know. We will say it Q, and the work which we are getting is W irreversible. Okay. Now, so who was talking about this reversible, irreversible engine? I think Anik was there, no? Right, Anik? You were talking about this thing? That what will happen if we'll take irreversible engine?
No, sir, I was not talking.
Oh, okay. Anyway, whoever is asking, he can participate. So anyway, Anik, what do you think? Which one is greater, WI or WR? Yeah, this
Sir, WR.
WR, right? Why? Because we have learned this that
reversible process, cyclic process, we get the maximum work.
Yes. So that we know. Huh? So we know that from our basic experience, the WI is less than WR. That we know. Okay, that we have seen. Now, let's say if you want to prove this in this whole, remember that the way we prove it here is like we try to prove a contradiction. The way we did it in the previous, not proof, but remember that this when we tried to prove this equivalence of Kelvin, Planck, and Clausius statement. That's how we did. So we are going to do the same thing here. So what we'll do is as follows. Now, let's say that what Carnot theorem 1 says is not correct. So let's say Carnot theorem 1 is false. If it is false, then I can write eta of irreversible engine is greater than eta of reversible engine. I am discarding the claim by Carnot, means first claim, this theorem 1. So if that is the case, then this is true. Eta I is greater than eta R. Okay. Fine. Now, eta I we can define as anyone? Wi by? Yes.
Q1.
Greater than WR by Q1. Okay. Now W1 I can write. W1 I can write Q1 minus Q by Q or by Q1. greater than this, I can write what? Q1 minus Q2 by Q1. If we solve it more, it will be simply it will be simply 1 minus Q by Q1. This is 1 minus Q2 by Q1, right? Of course, 1 get cancelled. Then there is a minus sign, so this so 1 get cancelled. And then, of course, if you do this minus plus, this sign will be flipped. So this Q1 get cancelled. Okay, what we get is Q is less than Q2. Okay, fine. Q is less than Q2. Okay, and we have already this Wi is greater than Wr. That we know. That reversible engine always does a larger amount of work than Wi. Right? And in other way also you can prove it, that since if you don't get convinced, there another way to say it is this way, that wait, how we can do that? You can do this way also. It's see, both are same statement basically. So even through this path also you can reach there. You can do this way, that Q1 equals to Q1, right? Q1 equals to Q1, and then here you are subtracting Q, and here you are subtracting Q2. So which one is great? So this will give us Wi, and this will give us Wr, right? Is it fine? So this will give us W as, oh sorry, both are not true. This we know from our experience. Sorry. Right now you just omit this. Just follow this one, otherwise it will be too much confusion. See, that was the claim, I think, through this, what I have written, that W irreversible is less than W reversible. Probably that's what we want to prove in Carnot theorem 1. I think so. Because see, this claim will give us what? This claim will give us, if you'll see here, it simply says Wi is greater than Wr. Okay, so that's what we have. This is the ideal thing which you want to prove. Okay, so that's that we know from our experiments. Right now, don't follow that. What we are saying? Let's say Carnot theorem 1 is false. It means eta I is greater than eta r. Means Wi by Q1 is greater than Wr by Q1. It means if you can cancel Q1 Q1. What we are saying is Wi is greater than Wr. Okay, which we know, which is not true, but then we want to prove it. Basically, what I should say here, that this we have discussed through example. You know that example which I discussed at a very early stage and today also, that we know that W reversible is greater than W reversible, but we know it through experiments. Today we are trying to prove it mathematically. This is nothing but Carnot theorem 1, simple. Okay, this is nothing but Carnot theorem 1. So one can write this way also, isn't it? Carnot theorem 1 says what? That this reversible engine has highest efficiency, and when you define efficiency, the denominator is same. So we are simply saying Carnot theorem 1 is nothing but W reversible is greater than W reversible. That's what we want to prove mathematically today. We said no, this so in order to prove it, we said that this claim is wrong itself. So either you say eta, so when you say this statement is wrong or Carnot theorem is false, either you say eta is greater than eta r or Wi is greater than Wr, both are same thing. So these are equal things. Okay, we are saying that this statement is not correct. We are discarding it. If you are discarding it, then reverse is correct. So either you write this or this, both are same. Is it fine, Anik? Does it make sense? That Nidhi, is it fine up to this point?
Yes, sir.
Yeah, so we have Wi greater than Wr, we have Q less than Q2. Okay, that's what we prove from this claim. Starting from this claim, we have reached here. Now what we'll do, see carefully. Okay, So rather than writing so much, I'll just write the important stuff. Oh, that's fine. Let it be. Now what we are going to do is as follows. See, if I'll ask you that what is the net, if now what you have to do, that you have to manipulate with this all heat transfer and work transfer, so that you don't affect the overall heat interaction from the reservoir. So I can always make a combined device. I'll combine it. Let's say there is a new device. This is our new device. Okay, this is our new device. How much heat this device? So what is the net heat interaction from from source? Anyone? Net heat interaction from the source?
2Q1.
No. Not net heat. How much net heat we are taking from the hot reservoir? See the diagram.
2Q1 minus Q1 plus Q plus Q2.
No. How much heat we are taking, net heat from the reservoir, a hot reservoir, T1. Anyone? It's clear in the diagram, no? How much?
2Q1.
0. See the direction. Isn't it? Oh, sorry. 2Q1. Sorry. Yes. We have to reverse the direction now before this. I'm very sorry. Yes, you are right. 2Q1. Okay, 2Q1. So we have to do very good. I'm very sorry. I got it. So whoever said, you were right. 2Q1. TH. TL. Very sorry. You are right. This is our reversible. This is our irreversible. Yes. Q1. And then this is Q2. Yes, 2Q1. I agree. Q1. And this is Q. This is our W reversible. W irreversible. We said Carnot theorem is wrong. That's what we are claiming. So it means we are saying eta I is greater than eta R, which is equivalent to saying Wi is greater than Wr. And what else we proved from algebra? That Q is less than Q2, I guess, right? Yeah, Q is less than Q2. That's so. Now again, so net heat interaction is 2Q1. Yes. Now what you do? You do this thing that since this engine is reverse, this Carnot engine is reversible. Okay, I can always flip that. I can make this Carnot engine as Carnot pump. So that's what I'm going to do. What I will do, rather than using it as a heat engine, I'll make a Carnot pump. So I'm reversing the direction. Okay. Why I can do that? Anyone? Because it's a reversible engine. For irreversible engine, you can't do it. But for reversible, you can do it because you know that exactly it can be reverted back. So now let's revert it. So what will happen? Now Q2 will be taken from here, right? From low temperature source. How we can do it, Nidhi? If we are trying to transfer heat from low temperature, what we have to do according to Clausius? Yes, Nidhi? What do you think?
Provide work.
You have to do work, right? Otherwise, it's not possible. So you are doing work. How much? WR, because it's a reversible engine. So same thing will be flipped. When it was working as a engine, it was delivering WR work. When it will work as a pump, you have to deliver same amount of work to transfer the heat from low temperature body to high temperature body. And what we are transferring is Q1. So since it's a reversible engine, we can revert it back. Now you can tell me, yes, Nidhi, now you can tell me how much is the net heat interaction with high temperature source? 0.
0. 1 minus Q.
Yeah. So if I'll make now, if by, so rather than now you can say it R pump. Now I'm combining these two devices. And I'm making a new device. So let's make the new device. TH TL. This is my new device, this black box. How much heat it is taking from higher source, from TH? Nothing. Okay. Then what else? See, if I'll ask you what is the net work output of this black box, what will say? Net work output.
WI minus
WI minus WR. Wonderful. So WI minus WR. Okay. How we can do that? So basically, this blacks in what will happen, that whatever WI you are getting, some part of this, since you need this WR, right? You need this, it's a single device, you need this WR. So what you will do, rather than going it from here, you will provide this WR from output of irreversible engine. So if you are giving WR here, net output will be WI minus WR. That's what you said. So the net work output of irreversible engine was WI. From that WI, WR I have given to this pump because it need work, and the remaining amount is coming as the net work output from this black box, the new device. So new device is delivering work WI minus WR, and how much heat it is taking from the TL, because from TH it's 0. From TL, how much heat it is taking? Anyone?
Q2 minus Q.
Q2 minus
Q2 minus Q. Very good. And what we have, so this is new device. And what we are violating now? Anyone? Where we have reached? This is what? PMMSK. This is violation of Clausius statement. You are transferring the heat from a low temperature body. You are taking the heat from the low temperature from a single body. Sorry, it's Kelvin Planck, not Clausius. You are taking the heat from a low temperature body, or a single body, no, not low temperature, high temperature. You are taking the heat from a single body and you are converting it into what? Which is impossible. That is what PMMSK is, perpetual motion machine of second kind, isn't it? You can get back to, because this is not possible. Because second law says that you will always lose some energy, whereas with our initial claim that Carnot theorem is wrong, and with the help of this, what the ultimate conclusion which we are getting is that we can convert heat into work using a single body, which is not possible according to Kelvin Planck. You need a sink also. I mean, you will lose some energy. So it means our claim was false. So this, it means since due to this violation of Kelvin Planck statement, or you can say this is perpetual kind of machine, which is not possible. So our claim was wrong. If our claim was wrong, then Carnot theorem is not wrong. Carnot theorem is right. That's how we prove. Okay. So what we have proven here? We have proven here that reversible engine will have always higher efficiency than irreversible engine. Anything anyone wants to comment? That's how we prove in this thermodynamics. There is no other way. It's not a proof, it's a way to convince you, to be very frank. Because we know from observation, we were already knowing, we already discussed from experiments. You remember those blocks experiment, or the experiment which I discussed with Sashank, that you have tables and then you are doing it reversibly. So that is the work volume mass. That we know already, that W reversible is greater than W irreversible. Just to convince you, this proof you'll find in books. That this you can prove by saying that this is not correct, this is wrong. So we have said this is wrong because both are same. Carnot theorem 1 is wrong, and then we reach something which is not possible according to the basic postulate of second law, which is that. I mean, there are many basic postulates, so it violates this Kelvin Planck statement. Okay, so it means this is wrong, and what is correct is eta R is always greater than eta I. Eta Carnot. Okay, that is one. Second statement. So what second statement says? Every Carnot heat engine between a pair of heat reservoirs is equally efficient. In simple means that if you have two reversible engines, Carnot engines are reversible engines. So now we'll say reversible engine. If you have two reversible engines and both are working under between the same reservoirs, their efficiency cannot be different. It will be same. Let's prove it. again you'll see that the approach is same. So second, so Carnot theorem 2. Let's go to new page. What it says, it simply says that let's say you have TH, or rather than TH, what is it? T1, T2, right? So let's say T1, T2. T1, T2, okay? And now you have two reversible engines. Reversible engine 1 and reversible engine 2, okay? Both are taking same heat so that you can compare Q1, Q1 from the source. What we want to prove? We want to prove that eta R1 is equal to eta R2. That's what we want to prove. Okay. Let's say that this claim is wrong. Okay, so this is not true. So what we are claiming? Our claim. What is our claim? Our claim is that let's say their efficiencies are not equal. So what we are claiming is, let's say eta R2 is greater than eta R1. That is our claim. Okay. Fine. So right now what we are saying, that this is correct and this is wrong. That's what we are claiming. Or rather than R2, R1, let's say R1, R2. Otherwise I have to change all because the way I have written the proof. Let's say it R1, R2. Unnecessary. Otherwise I have to put more effort. It will waste. Let's say R1 greater than R2. That's fine. You can say whatever you want to. R2 greater than R1. You can prove in both ways. I am saying eta R1 is greater than eta R2. You can try for eta R2 greater than eta R1. Okay. Right. So that's fine. Now, if we are saying that, we are simply saying that WR1 is greater than WR2, no doubt, because the denominator is same, right? Because eta R1 is nothing but WR1 by Q1. This is also Q1. Okay. So Q1 get cancelled. So this is, of course, WR1 is greater than WR2. So let's encircle this. This we have according to this claim. Then what else? If you want to write this eta R1, you can also write 1 minus, let's say that this R2 is rejecting Q2 and this R1 is rejecting Q. Okay. Just a minute. Q. Fine. Great. So you can write eta R1 as 1 minus Q by Q1 and greater than 1 minus Q2 by Q1. Okay. Yeah. Fine. So 1 minus Q by Q1 and 1 minus Q2 by Q1. Do the algebra. Ultimately, what we will get is Q2 is greater than Q. Okay. So that's what we have. Okay. Now, since both engines are reversible, we can flip any one of them. Or rather than flipping, what we can do is, rather than flipping, or we should flip. Yeah, we should flip it. Otherwise, you won't be able to do it. Again, it will be 2Q1. So let's say we are flipping this this one R2. Let's flip it. Okay. So if we flip this this R2, and why are flipping it? Because if you remember that WR1 is greater than WR2. So it means that WR1 minus WR2 will be a positive work which you can provide to a pump, and then you can transfer heat from low temperature to high temperature body. So now again, what I am doing first, since it's both engines are reversible, I can flip any one. I am flipping R2 because amount of WR1 is greater than WR2. So let's flip it. Okay. So what will happen now? This is Q2, and then we need some work. Actually, we haven't written work. No? So when it was not flipped, This was giving us how much? WR1. And this was giving us WR2. We have flipped it, so it needs WR2. And Q heat is, this whole heat is going up. So now you guys help me. We have seen the last thing. So what we should do? Let's say Sneh, what we should do now? We have flipped it. We have made it pump. Now what we'll do?
We should like WR1 minus WR2.
So first make a one device, right?
Yes, sir.
So let's encircle this. Yeah, you're right. I'm just helping you. So let's make one device. So this is our new device. Okay. And in this new device, since we need WR2 for this R2, so let's say from WR1, we will give WR2 to this. So the remaining amount will be WR1 minus WR2. And that we know WR1 minus WR2 is positive. What is net heat interaction from T1? Nothing. Q1 in, Q1 out. Please go on. Yeah. So again, what we have, and what is net heat interaction from T2? So this is Q2 minus Q, right? So you can remove this also, because our combined equipment is taking Q2 minus Q. So what we have again proved? PMMSK. So our claim was wrong. This is wrong. Since our claim was wrong, the original claim was right. Okay. So the overall summary is that these all things we have done just to tell you that reversible heat engine have always higher efficiency than irreversible heat engine. And then we have to find out the reversible heat engine for your calculations. The ideal one is Carnot engine. Carnot defined such. One can define other kind of reversible cycle also. No problem. Okay. And if you find out the efficiency of that reversible cycle, that will also come out to 1 minus TL by TH, undoubtedly. Rather than isothermal and adiabatic, you can think something else. Think something, but it has to be reversible. So that you know the PV relation and you can calculate it. Or if you don't want to go for the mathematical derivation, you can do plenty of experiments. Okay. Your engine should work in a reversible manner. It's need not to be always isothermal adiabatic. No, it can be anything else, any other process. Okay. But if it is reversible, if you have done all the steps reversibly, its efficiency will be always equal to 1 minus TL by TH, which is also equal to one of such engines which is known as Carnot engine. That's all. And if you have any irreversibility in the engine, which we will see, don't worry. Irreversibility means your all steps are not reversible. Like if you see the real heat engine in our car or vehicles, the expansion is sudden. When the heat, when this fuel gets burned, it expands the piston expands very fast. The gas expands very fast. So it's a irreversible expansion. So of course our engine's efficiency is quite less than, significantly less than Carnot engine. Okay. Okay, and one can always argue what is why not the Carnot engine efficiency is 1. What is the answer? Or 100%? What is the answer? How you will convince that person that why not the Carnot?
Perpetual motion machine cannot be.
Yeah, or simple second law. Carnot statement is nothing but second law. We can't prove a law. It's observation. That's what nature tells us. That even if it's reversible heat engine, it will always lose some energy to the lower temperature or surrounding. Okay. Okay. So this is all about Carnot theorem. We know about reversible, irreversible heat engine, and we know that the highest efficiency is reversible. What will the next in this? Along this line is now more fundamental thing. And now we are very close to defining entropy. I'll take 5 minutes and then I'll again meet tomorrow. Tomorrow we'll certainly define entropy in classical thermodynamics. Once we'll complete that, then we'll define it from microscopic approach. A small detour, that's all, not in very detailed manner. Okay, great. What I'm leaving for you, that I'll tell you, that is called something is called that will be homework, not today, some other day. Thermodynamic temperature scale. That as a homework. And someone will tell us that how much he understood. I'll ask multiple people. That you have to do by your own. Thermodynamic temperature scale. Why we need it? Because there are already temperature scale, degrees Celsius and this Fahrenheit. Then what is this thermodynamic temperature scale? And what is the beauty of this? Okay, that I leave on you. Well, what is the next agenda under this topic is as follows. Yeah, a few small things, and then we'll reach to this statement of second law under definition of entropy. Before that, few small things which are more, very trivial but very practical. You know that you use refrigerator. Let's say a refrigerator. So what a refrigerator does, if you define it in terms of simple schematic, does it take work or does it deliver work? Anyone? Refrigerator
Takes work.
Takes work. So you give some work. And then what is the refrigerator function of refrigerator?
Eject heat.
Eject heat. So let's say there are some food items. This is a sink. TL. So it extracts heat from the lower temperature body and it ejects it to the surrounding, which is at higher temperature. That is the purpose of refrigerator. Okay. So there is something called coefficient of performance. If you have seen it, very good. Not, then you can see coefficient of performance. How I will judge the performance of a refrigerator? Let's say this is QL, this is QH. Yes, you try. This is a bit trivial, so I leave it on you. What should be the definition of, if you want to define the performance of refrigerator, not efficiency?
Heat ejected out by work given.
So ejected out means which one? QL and QH? QL or QH?
QH is the heat ejected.
No. The efficiency depends on how much you can extract this QL. The more more will be the QL.
Oh, sorry. Yes, sir. Yes.
Will be the
QL.
colder will be your this thing. This. Okay. So COP for a refrigerator is QL by W input. Okay. If you want, similarly, if you want to define a heat pump, you don't see heat pump here, but if you go to cold countries, there is something called heat pump. The purpose of heat pump is to keep the room at higher temperature. So there what happens, the surrounding, the outside ambience is really cold. TL, this is our outside your room, let's say outside the room, very cold, and you want to keep your room hot. So that heat pump is mainly used in cold countries. So then again, heat will be extracted. Sorry, heat pump. So what will happen here? Here, yeah, fine. So what we are trying to do, that we want to, so this is outside the room and this is our room. So if you want to keep our room hot, we want to give heat to our room. So this is QH. And you are extracting heat from the surrounding, which is at lower temperature, TL. So then what we have to do? We have to do work or we will get work?
We have to do work.
We have to do work. This is W. Now define anyone, maybe Bhavna, if you are there, define coefficient of performance for heat pump. COP of pump. What do you think? See, what is our agenda? What is our, what we want? We want to keep our room hotter, right?
Yes, sir.
So how will measure the performance? QH through QH or through
QH by W.
That's simple. Okay, so it's very trivial, but sometimes students make mistakes. Okay, now 2 more minutes and then you can leave. 1.6 or 1.7. Okay, see, if you remember, what we have proven is we have proven that for Carnot cycle, now I will not write Carnot, okay? We will write for reversible heat engine or reversible cycle, both are fine. Okay, for reversible cycle, we know that eta is equal to 1 minus anyone QL by QH, and this is also equal to 1 minus TL by TH. If we'll take these two expression, what we'll get? We will get QL by TL plus QH by TH is equal to 0. Okay. This is for reversible heat engine. Now what will happen if we'll take a irreversible heat engine? So I think this will take time. Okay. We will meet tomorrow, that we'll see that what happened in case of. So what we have seen that for reversible heat engine, this is always true for a reversible heat engine, that QH by TH minus QL by TL equal to 0. If someone wants to write, someone can write summation of QI TI equals to 0, where TI is the temperature of the reservoir and engine boundary. Okay, that we'll see in detail. But what will happen if we take irreversible heat engine? And QI has to maintain its sign. If you are giving to the system, it's plus. If you are taking from the system, it's minus. Okay, so that we'll see. Yeah, so tomorrow we'll see that what will happen to this summation of QI by TI when we take a irreversible heat cycle, and then how we can go for rather than this kind of discrete Carnot engine, how we can go to more general cyclic process. So that we'll do tomorrow. That is the agenda for tomorrow. Okay, with this, thank you to all of you. I'll yes, please follow.
Sir, actually now what happened that maths Frau has told that he will take classes regular on Thursday.
Yeah, no problem. Okay, that's fine.
Otherwise, you could take continuous 2 hours on Wednesday itself.
Sorry, 2 hours? Is it? But you don't have class after 2?
No, sir. Like we don't have class from 11 o'clock. Like you can take.
Oh, okay. Then yeah, that's a wonderful. So should we continue today or no?
Not today. Like from next week.
People are not ready today. Okay, that's a good suggestion. So on team, I am going to teach only till 24th February. So till 24th February, and then I'll finish my part. So we'll increase our pace a bit. So okay, fine. So then from next Wednesday, it will be a 2-hour class. Can we make up this today's 1 hour for only for this week on Saturday?
Yes.
Okay?
Yes.
Okay.
Yes.
Yes,
So
sir.
okay, so we meet on then Friday at 9. Tomorrow there is no class. Thank you. Thanks. I'll upload all these slides combinedly, okay? Because slides are a bit scattered and I'm telling too many things. So I will place it nicely and then I'll share. Okay. Meanwhile, you can go through the downloaded lectures. Thank you. Thanks.
Okay, sir. Thank you, sir.
Thanks.
Thank you, sir.